Hello, what we're going to do here is find the volume of a solid using cylindrical shells, the cylindrical shell method. And what we're starting off with is a function that's not really what I would call an elementary function that you would, and for which the graph you would memorize in pre-cal class, but it's a good graph to know about. It's essentially it's very close to being a bell-shaped curve. It is, but to make the area below that one, we would have to multiply by a constant. But essentially, it's something that we would call the bell-shaped curve. You can find out, you sketch this graph even better, much better, if you find critical numbers and inflection points. But that's another topic. We're starting at 0 and we're going to 1 right here, and so we're essentially looking at this. This region right here. Now, so again, what I'm saying is here I'm giving you the graph and we'll go from there. I don't think the directions actually even ask you to sketch the graph. So here we go. Let's call that R. Maybe I'll use a reverse negative color there. Okay. So we have this guy as y equals e to the negative x squared, and we're going to rotate this around the y-axis, and that's important for us to see. Now, the reason we're going to use the shell method is that this function is expressed as this is a function of x. Y is a function of x. Now, if we use the dishwasher method, we would have x equals f of y. X is a function of y. But here we have y as a function of x. And going around the y-axis, when y is equal to a function of x, is when we can try to use the shell method. I mean, it's going to result in an integral, and if the integral doesn't work, you don't want to, use that method. But this is a pretty well set up. It was a little bit, hey, well, sketch the graph. Was that difficult or not? I mean, sketching the solid, but we're essentially moving on to the formula for our shell method. So the shell method formula, where we have, let me just write this down. So I have a to b 2 pi x f of x dx. So this is when I'm rotating about the y-axis. I mean, it's in context of this problem. So simply all we're going to do is plug in the numbers 0 to 1, 2 pi x, and e to the negative x in the function e to the negative x squared dx. Notice that we integrate from 0 to 1, even though after the rotation it goes all the way from -1 to 1, we still are only integrating from 0 to 1. So I think that actually part of this, why it's sort of a cool problem or interesting problem, is to enable to do this, for us to integrate, we'll have to use U-substitution. So it's a good problem just to go over this. So we'll use U-substitution. And I'll let u equal e to the negative x. Sorry, that's not right. Not at all what I want. U equals negative x squared, and I take the derivative, and I get negative 2x dx. So du equals negative 2x dx. So negative 1/2 du equals x dx. And so when I write this down, I have 2 pi, but let me just put this over like this, x dx. This x dx becomes negative 1/2 du. This guy right here, negative x squared, is u. So we get integral 2 pi e to the u negative 1/2 du. What I'm going to do is I'm going to change the bounds, because this is a definite integral, and so I'm going to change the bounds. I wanted to move everything. Let's see if I can do that. Maybe not. Not all that successful, but I wanted to move it so I have more space. Okay, so let's change the bounds. And the way I do that is when x equals 0, u equals -0 squared. So u is a function of x. So if I put in the bottom bound, what I'm talking about is the bounds of integration. So I put the bottom bound as 0, lower bound is 0. I think that's the correct expression is lower bound, not bottom bound. And then I put the upper bound as 1. So when I put x is 0, u equals -0 squared is 0. When I put x is 1, u equals -1 squared, where we follow the order operations of taking the exponent first and then squaring. So we want to make sure we do that. And I feel like I had something that got moved maybe in the wrong place. Oh, here we go. It's dx right there. Okay, so I'm changing these bounds, and just with the idea of fitting this in one page, I'm going to write this. Okay, so we were going from 0 to 1, but 0 corresponds to 0, 1 corresponds to -1. So I have the integral 2 pi times -1/2 makes negative pi from 0 to -1 e to the u du. I like having the number that's the smaller number, which is -1, -1 less than 0, the bound that's the lesser number on the bottom, and I'm going to do that. And when I do that, when I switch the bounds, so I'm switching the bounds to put the -1 on the bottom. So when I switch the bounds, I change the sign from negative to positive. You don't have to do that, but I like doing that. Okay. Then I integrate, and I have integral of e to the u is e to the u, and I plug in -1 and 0. So I have pi e to the 0 minus e to the -1. So this will make pi 1 minus 1 over e. My final answer looks not as neat as it could be. All right, so sort of saw the next problem below that, but okay, that gives the answer, and that finishes up the video.